this together, and we're going to try to actually look at how to graph a rational function by hand. So here I have the rational function y equals x squared plus x minus 12, all divided by x squared minus 4 that I want to look at to try to graph. So I'm going to break this down into a process for you. The first thing that I want to do is identify the horizontal asymptotes. We talked about how to do that in other videos. It has to deal with the degree of the numerator and denominator. Once we do that, then we will determine if this graph is going to cross its horizontal asymptote or not. It may or it may not. We'll look at that here later on too. Then we will identify any vertical asymptotes and holes from our points of discontinuity and determine that based on what type of discontinuity we had. Then we will find the x-intercepts, followed by finding the y-intercept, and then we will just determine a few more points on our graph in our interval so we can get a better idea for what this thing is going to look like. And then finally, we'll actually go to the graph and we'll put all of those things on there, starting with the asymptotes and then the intercepts and then our additional points. So let's take a look at that now, and let's start off by trying to figure out what our horizontal asymptote would be for this function. So trying to find the horizontal asymptote, we have to consider the degree of both the numerator and the denominator. So here I look at this and I see the degree of the numerator here is 2. The degree of the denominator is also 2. When the degree of the numerator and denominator are equal, the horizontal asymptote will be the horizontal line y equals the fraction of the leading coefficients of your numerator and your denominator. The leading coefficient of this numerator would be 1. The leading coefficient of this denominator is 1, and 1 over 1 would just be 1. So the horizontal asymptote line for this rational function is the horizontal line y equals 1. So next we want to determine if the graph of this function is going to cross its horizontal asymptote line. The graphs of these rational functions certainly can cross their horizontal asymptotes. They cannot cross vertical asymptotes, but horizontal asymptotes they certainly could. So the question here is, does the graph cross the line y equals 1? And the way we're going to figure that out is we're going to go ahead and plug 1 in for the y, and then try to solve for x and see if we get a solution to that equation. So we have 1 equals x squared plus x minus 12 divided by x squared minus 4. So to go ahead and solve this, I'm going to multiply both sides by x squared minus 4 to get that out of the denominator over here. When I multiply that side by x squared minus 4, I'm just going to get x squared minus 4. And on this side, I would just be left with x squared plus x minus 12. I don't know, maybe it's easier to think of it as like this is 1 over 1, and all I was doing was cross multiplying. So that times 1 was that, and 1 times that was that. And now it's just a matter of solving this equation. I can subtract x squared on both sides and be left with negative 4 is equal to x minus 12. And then I can add 12 on both sides to be left with 8 equals x. So this graph actually does cross its horizontal asymptote line, and it should cross the line y equals 1 at the point 8, 1. So when you graph this, you should know wherever you draw your horizontal asymptote line in, you need to have a point intersecting that horizontal asymptote line at 8, 1, showing where the graph is crossing that horizontal asymptote. Next, we're going to try to identify the location of any vertical asymptotes or holes in the graph. To do that, we need to know our points of discontinuity. We need the values that make the denominator equal to 0. Whether or not that factor also exists in the numerator is important to determining what type of discontinuity we have, whether it's removable or non-removable. So what we're going to need to do now is go ahead and factor both the numerator and denominator of this rational function. To do that, we will end up with y equals our numerator right here. I need numbers that multiply to negative 12 and add up to 1. That would be positive 4 and negative 3. So x plus 4, x minus 3. And in my denominator, I recognize that as a difference of squares. X squared minus 4 should factor as x plus 2, x minus 2. Looking at this factored form, I see that the x plus 2 and the x minus 2 in the denominator do not get canceled out completely from the denominator by any of the factors in the numerator, so they are not removable discontinuities, meaning that these are both non-removable discontinuities, which would represent vertical asymptote lines. So this graph has vertical asymptotes of x equals negative 2, that's what I get when I set this factor equal to 0, as well as x equals 2. That's what I would get when I set this factor equal to 0. So again, if I show the work for that, so I do x plus 2 equals 0, and I get x equals negative 2. Here I get x minus 2 equals 0, and I get x equals 2. That's the work that I was using to figure out the location of those vertical asymptotes. Since I did not have any factors that got canceled out completely from the denominator, I did not have any removable discontinuities, and because of that, I have no holes in the graph to consider. Next, we want to locate the x-intercepts of the graph. Remember, to find the x-intercepts, you plug 0 in for y. So we have 0 equals x squared plus x minus 12 divided by x squared minus 4. So now I have to ask myself, well, when is a fraction equal to 0? A fraction is equal to 0 when its numerator is equal to 0. So if I want to know when this fraction equals 0, I'm really just trying to figure out when its numerator, x squared plus x minus 12, is equal to 0. I actually just factored that a second ago as x plus 4 and x minus 3. So I can set each of those factors equal to 0 and get that x equals negative 4 and x equals 3. So my x-intercepts are the points negative 4, 0, and 3, 0. Those are the points where the graph would be crossing the x-axis. Now that we've found the x-intercepts, we'll move on to finding the y-intercepts. To find the y-intercepts, I will plug 0 in for x and figure out what I get for y. When I plug 0 in for x, all of these terms that contain x will just vanish from the problem. And I'll just be left with negative 12 in the numerator and negative 4 in the denominator, which is equal to 3. So this graph should be crossing the y-axis at 3 on the y-axis. That would be the point 0, 3. Would be the y-intercept of the graph of this rational function. Okay, so now that I've found all of that information, and I found my horizontal asymptote to be the line y equals 1, and then I found that the graph will cross that asymptote at the point 8, 1, I've added that to the graph here. I've also displayed my vertical asymptotes of x equals negative 2 and x equals positive 2 here, as well as my x-intercepts that I've just found of negative 4 and 3, and most recently my y-intercept of positive 3. And you can see I have all of that information on the graph, but I don't really think that I get a very accurate picture of what the graph of this function is going to look like yet. So I need to plug in some other values, maybe over here in this range, something in this interval from negative infinity up until negative 2 to see what's happening there. And then maybe some more values in this interval from negative 2 to positive 2 to see what's going on in between there. And finally, some more values over here in this other interval from 2 to infinity. So let's go ahead and do that now. Pick some values in those intervals and see what happens. And then we'll add those points to the graph and see if we get a better idea for what this graph should look like. Okay, so now we're going to try to find some additional points to make our graph maybe a little bit more accurate and give us a better idea of what's going on. So I've just selected some values in those intervals I was talking about earlier. In that interval from negative infinity up until negative 2, I've selected negative 8, negative 3, and negative 5 halves to just go ahead and plug in to get some more points there to see what that looks like. And then that middle interval from negative 2 to positive 2, I went ahead and selected negative 1 and positive 1. And then in the other interval from positive 2 to infinity, I've selected 5 halves to get one pretty close to the asymptote, and then 6 as well. I already have an additional point where it crosses the horizontal asymptote line of 8, 1 in that interval. So that's why I only did 2 over here in this interval instead of 3 like I did over in that interval with that. So to save time, I trust that you could take these values, plug them in for x, and then simplify to figure out the y coordinate. To save a little bit of time so that you don't have to watch me do that in this video, I've already done that. I've plugged negative 8 in for the x. When you plug negative 8 in for the x, you end up getting 11/15. So we have an additional point of negative 8, 11/15 that we can add to our graph. When I plug in negative 3, I get negative 6/5. So again, I have an additional point of negative 3, negative 6/5 that I can add to my graph. And when I plug in negative 5 halves, I get negative 11/3. So I have another point of negative 5 halves, negative 11/3 that I can add to my graph as well to get a better idea of what's going on over in that branch of this rational function. In that middle interval, I'll plug in negative 1 and positive 1. I've already done that. When I plugged in negative 1, I got 4, giving me the additional point of negative 1, 4. And when I plugged in positive 1, I got 10/3. So giving me an additional point of 1, 10/3 with that. And then finally, over in the other interval, from 2 to infinity, I've selected 5 halves. Looks like when I plugged in 5 halves, I got -13/9. So 5 halves, -13/9 is another point on my graph. And then finally, plugging in 6, I got 15/16. So the point 6, 15/16 should be on the graph as well. So let's go ahead and add those to the graph, take a look at what that gives us, and see if we can start to see the shape of this taking form. If you don't, you could certainly go back and plug in more points in those intervals until you can better see the shape the graph is. Okay, now that I've added those points to the graph, I can start to see the graphs taking shape a little bit. Over here, I think I can kind of see how this branch is forming as it's approaching the asymptote line. Same thing over here on the right. I can kind of see how this branch is starting to take shape over here. Maybe in the middle, you're maybe a little unclear on what's going on still. I know what's going on there, so if you don't quite see it, it's going to kind of take a little bit of a U shape in here like this. If you don't see it, maybe you need to click some more test points in that interval, use some fractions in there to see that. So there's where we're at with our points in there. I think that's enough to get a reasonable idea for what this graph looks like. I've already graphed it, so I'm just going to use the technology here to go ahead and like draw it through those points as best I can. So go ahead and turn that on real quick. So you can see that. There's what the graph would look like. You can see it passing through all those points, behaving how it should near the asymptotes and everything. So there's the graph of that rational function. It's a rather drawn out, intense process. Lots of different steps involved there, but you can create some reasonably accurate graphs by hand of some of these rational functions. So that's how you do that.